All right, so guys, this is objective 6.1a. It has a part B, which I will teach tomorrow. Today's topic is sequences and series, the basics. What are they? Mainly, what are they? And how do you find numbers in a series or numbers in a sequence? So you will be successful when, number one, you can compare and contrast a sequence and a series. You know what's the same about them, you know what's different, and you can explain it to me. And also, really important, that you don't mix them up and define a series as a sequence and a sequence as a series. Don't mix them up. Make sure you know the difference. Okay? Objective 2, you can read the notation for a sequence. Because let me tell you something, you already know all the math that goes with it. Pretty much from now on, you're just going to see this notation and it'll look really complicated. But it's not as soon as somebody explains to you what it means. Like, oh, I can just do the math for that, no problem. You just had to tell me what that meant. And then 3, you can find values in a sequence and sums of a series, which is our objective. Our main objective is to find a number in a sequence, find a term in a sequence. So these are the 3 objectives. By the time you leave, you should be able to successfully solve problems and explain and define sequences and series. Okay, here we go. Are you ready? So what is a sequence? What is a sequence? So I'm going to define it first, and then I will give examples. So a sequence is a function. That should sound familiar, right? Whose domain which we know is the set of what variable is in the domain? The x's. But usually in a sequence, you won't see it as x. A lot of times you'll see it defined as n or possibly k. It depends. But it's a function whose domain is the set. Whose domain is the set of natural numbers. So here I'm being technical and I'm being all math teachery. What are natural numbers? Tell me you know. Exactly. Natural numbers are your counting numbers. So it's the set 1, 2, 3, and on and on and on to infinity. You're counting numbers. And they're always the same. Okay? Always the same. Now, sometimes we get a little confused with notation. So here's an example of a sequence. We're going to do an infinite sequence. 1, 3, 5, 7, infinity, and on and on and on. We call this an infinite sequence because it goes forever as the ellipse eludes. That pattern continues forever and ever. Another example could be the set of numbers -2, +4, -6, +8. No ellipse. No ellipse. What do you think that would be named? It's certainly not infinite. Drop the prefix. It's what we call a finite sequence. Now I'm going to tell you something that I'm not going to write down, but I suggest you write it down in the margins. A series is always indicated by a list of numbers separated by commas. Well, that seems pretty basic, Mrs. Frame. That's just what you did. Well, I'm telling you, because you have to know the difference between a sequence and a series, that commas go in sequences. They don't go in series. So it's a list of numbers separated by commas. So I wonder if anybody's questioning my second list, my finite sequence. Because I told you it's a function whose domain is a set of natural numbers 1, 2, 3, etc. But my list has negatives and positives. Is anybody questioning that? Okay. Well, let me explain. When I see a sequence like this, 1, 3, 5, 7, etc. These are what we call the terms in the sequence. That's my Y. So I want you to think of this like a table of values. Usually we do a table of values this way, right? Vertically. I want you to think of this as a horizontal table of values, where the top number tells you the position, and the top number is your domain. So the number in position 1 is 1. What's the number in position 2? 3. What's the number in position 3? And the number in position 4? 7. So a sequence is still a function whose domain is the set of natural numbers, because you are looking for numbers in certain positions, and you can't have a number in position -2, right? You can either be in first place or you can be in last place, but you can't be in -2 place, right? You can't. So this is the domain. So let's put here n. It's the nth term, and let's put the rule that tells us how to find the number that goes in that term. I think this is 2 times n position minus 1. So let's think about it for a second. If I plug in a 1 to my rule, that's my position 1. What's 2 times 1? Minus 1 is? Let's go to position 2. 2 times 2. Minus 1. 2 times 3. Minus 1. Okay? So the domain is all about the position of the number. Where is it positioned in the list? Is it in 17th place? Is it in 31st place? Okay? So that's what the domain is about. All right, I do want to talk about a constant list that looks like this. If I have this list, 5, comma, 5, comma, 5, comma, infinite. We call this a constant sequence. A constant sequence. There's no variable. Position 1 is 5, position 2 is 5, position 3 is 5. It's constantly 5, unchanging. There's your constant sequence. So basically, we could say that this is the A sub n equals 5. There's the rule. It doesn't matter what position it's in, it's a 5. Okay? So there's our definition of sequence. Now let's do some practice. The question says to write the first 6 terms of the sequence that's defined by the function f of n. You know what? I'd like to change this to say A sub n is equal to 3n times n minus 1. So we're given a rule, and we have to find the first 6 numbers. So what number's in position 1? What number's in position 2? So let's go up here to our position row, our domain, which is the set of numbers 1, 2, 3, 4, 5, 6, position 1, 2, 3, 4, 5, 6. And let's plug those values into our rule to determine what the first number in our sequence is. So we'll do a sub 1 is equal to 3 times 1 times 1 minus 1. Just replacing the n's with 1s, because that's what it says. So we do a little math. That's 0 times 3, which is 0. So the first number in our sequence is 0. And it's a sequence, so I'm going to put a comma. By the way, is this infinite or finite? I want the first 6 terms. Is that, can I count that? Yeah, I can't count infinity, but I can count this. So it's definitely finite. Let's do the next one. A sub 2. So we're just going to replace the n's with 2's. This is not foreign territory, is it? Right? This is pre-algebra, I think. So we plug in a 2. So that's 2 minus 1 is 1, and 6 times 1 is 6. So the second number in our sequence is 6. Or the second term in our sequence is 6, and we call them terms. A sub 3 is equal to 3 times 3 minus 1. I'm just giving you time to write it. You don't have to highlight it, of course. So what? That's 9 times 2? 18. So the third term in our sequence is 18. And you may think that you've got a pattern going here. You don't think that's enough to develop and help us pick the rest of them. We're going to have to stick to our rule and find the a sub 4, which is 3 times 4 times 4 minus 1, which is 12 times 3, which is 36. So that's the fourth term. A sub 5, quickly. 3 times 5 times 5 minus 1. That's 15 times 4, 60. So that's our fifth term. And then let's do a sub 6. So 3 times 6 times 6 minus 1. So 18 times 5 is 90. And so our series is 0, 6, 18, 36, 60. And not our series. That is wrong. It is not a series. It is a sequence. And it is finite. Okay? So there we have a visual that helps you to see the first 6 terms of a sequence when our domain is 1, 2, 3, 4, 5, 6, because it's the first 6, and there's our sequence, our output. All right, let's go to the next one. So the next one asks you to find the next term in the sequence. And so I am going to ask you first to fix this little typo over here. There's a typo that says x plus 2b, x plus 3b. I didn't want it to say that. I wanted to say x plus b plus x plus 2b plus x plus 3b. If you could fix that, please. And x plus 4b, just in case you decide to get ahead. Right? Now, I'm going to model for you how I still attack these problems. I still will see a sequence, and when I'm asked to find the next number or the 11th number or whatever number I'm asked to find in the sequence, I will make the table. And I will put the positions 1, 2, 3, 4, 5, and 6, because I need to focus. 6 is the number I'm working on a number 6. I'm doing something to a number 6 to get the 6th term in my sequence. And I will label the top version my N, or the top row my N, and the bottom my A sub N. Sometimes it's K and A sub K, but it's the same thing. So without the rule being provided, what strategy do you use? Anybody? What do you mean by that? Okay, so what do you try? How do I determine what the next one is? What do you think, Jonah?
I'm thinking it looks like it's A times 3 minus 1 so far. I've noticed something like that.
Okay.
I've noticed it's worked with most of them.
And that's because what's happening every time? Every time, right? It's going up 3 every time. You see, that's a constant thing. So we call that a common difference. And when we see a common difference like that, typically we know it has a common difference of 3, that this is an arithmetic sequence. And there's a formula that'll help you develop the rule, which I'll teach you on Friday. But when you see a common difference, it does help you to figure out what the next couple terms are. So the next one would be 14 plus 3. So the 6th term in the sequence would be 17. And that's all you're being asked to do right now. You are not being asked to come up with the rule. However, you are right, Jonah. It is 3 times n minus 1. He's totally right about that. So good job with that. Okay, let's look at the next one. Again, you have a sequence, and you're asked to find the next term. So again, just to reinforce the notation, and to reinforce that you're talking about positionals. This is your first number, your second number, third, fourth, and fifth term. We're looking for the 6th term. So the top is our domain, our natural numbers, 1, 2, 3, 4, 5, 6. Our bottom is our range, our output, your A sub n. So I'm wondering if by adding the positions in the top, you see the pattern immediately, like a correlation between position and output. 1 is 1, 2 is 4, 3 is 9, 4 is 16, 5 is 25. Do you see it? What would 6 be? 36. So sometimes without the position at the top, it makes it a little harder to see the pattern. Now, if you were not looking at it in that way, which is okay, you might see that it's going up 3 and up 5 and up 7 and up 9. So you could use up 11 to help you find that. Okay? I would say that if I wanted the nth term, what I would do is square the position. So if I were to now ask you, without you continuing the pattern, what's the 10th number in the sequence? It's 100. You're right. If I asked you, what's the 13th term in this sequence? 13 squared, which is 169. Exactly. So there is something to be said for recognizing that you're doing math with your domain, 1, 2, 3, 4, 5, 6, to develop your pattern. And if you can see the pattern, it helps you to find answers more quickly. Let's look at this last one. And we won't do the table again, but I would love to see you using the table on your homework just to reinforce what the values mean. Okay, so here we have the pattern x plus b, x plus 2b, x plus 3b, x plus 4b. So the next one would be x plus 5b. You can see it. I hope you can see that. Okay, so the first one was a common difference. By the way, it was arithmetic. The next one was a geometric sequence. We'll talk about that. I'll teach you that one on Monday. Right? Right, we're moving on. So now we're going to talk about what's the recursive definition of a sequence. Okay, so to know that, you have to know what recursive means. Anybody know? Recursive. Happens again. Re means again and again, right? Cursive, recurring all the time. And it builds on itself. So my definition of it is a recursive definition of a sequence. It's created by giving the first term. I'll tell you what the first term is in the sequence. And then I'll give you a rule to show you how to obtain the next term. And then you keep building from one term, you plug it in and you get the next term. And then you take that answer and you plug it in and you get the next term. And you just have to build, and it builds on itself. It's like a fence, a brick fence. You have to have the bottom ones to get to the next layer, right? And then you have to have the next layer to get to the third layer. So it's just building on itself. And so I've kind of color-coded here. The first term would be considered your A sub 1. And then the rule that shows you the next term would be the rule, the n plus 1th term. This is in the definition, whereas this is more in words, my definition, just to help illustrate. But that's term 1, and that'll be term 2, and then you'll build term 2 to term 3. Okay? So recursive, builds on itself, builds on itself. Okay, so here we have some information. It says, assume that each sequence is defined recursively. Builds on itself over and over again by the same rule. Assume, so we get to assume. Find the first 4 terms of that sequence. So I'm looking for a finite sequence. So here's my A sub 1. So I'm going to come over here and I'm going to fill out my table. Position 1, position 2, position 3, and position 4. The first 4 terms in my sequence. And my A sub 1 is 5. We were told that. We know that. That's our A sub 1. And our rule is to get to the next number, we're going to take 3 times the number before and subtract 2. Here's what it means. So we have A sub 1 equals 5. So to get to A sub 2, what I'm going to do is I'm going to take the A sub 1 plus 1, that's this part right here, and I'm going to plug in the A sub 1. So 3 times 5 minus 2. I'm just doing this rule right here. So to finish that out, that's the A sub 2 is equal to 13. So I fill it in, and I'll make my little series here, my sequence, 5, 13, comma. All right. Now I have to use 13. So now I'm going to use the A sub 2, and I'm going to get to the A sub 3. So now I have the A sub 2 plus 1. So to find it, I take the A sub 2, which was 13, and I plug it in for my n, and I get my A sub 3 is 37. So I put that in my little finite sequence down here, and I go to my very last one. Anybody want to tell me what I'm going to write in the next line? A sub? No. Look at how I wrote it. 3 plus 1, which equals times 37. There you go. Minus 2. So that, if I now do the math for that, that's my A sub 4, which is 111 minus 2, 109. And there we have it. Our finite first 4 terms of the sequence using the recursive rule that helps us to determine that. So it builds on itself. So could I find the A sub 10 right now? Right now. Yeah? You know what the A sub 9 is? You don't, right? So you can't get there until you build the A sub 5 and the A sub 6. And so these ones you have to build. At some point, you might see a pattern that helps you to determine that. All right, let's move on. So that's recursive. Now we're going to talk about a series. So we've been talking about a sequence. Sequences are listed numbers separated by commas. This is a sequence. It could be finite. It could be infinite. And it always has a domain 1, 2, 3, 4, 5. Okay, so what is a series? What the heck is a series? A series is formed by adding the terms in a sequence. So basically, you're switching out commas for addition signs. Basically, that's what it is. So for example, we could have an infinite series. I'm going to use an infinity sign. An infinite series could be 1 plus 3 plus 5 plus 7 plus infinity. Same pattern, different symbol between them. A finite series could be 2 minus 4 plus 6 minus 8 plus 10. Done. Now that's what we call an alternating series because it's switching signs. It's 2 plus negative 4 plus 6 plus negative 8, but I'm not writing the plus. You guys get it? Okay. So that's a series. So what's the difference between a sequence and a series? What? Yeah. Sequence uses commas in your list, and series uses addition. You're adding your list versus just listing your list. Okay. All right. So that's a series. So let's take a look at this question. It says, find the sum of the first 5 terms of the sequence with the given general term. Seems complicated. I'm going to give you some help with this. So you know that at some point you're going to find the first 5 terms, right? So you're going to find, so we're going to put this as our x. So we're plugging in 1, 2, 3, 4, and 5 because we want to know what those first numbers are. So this number down here is going to be our output, right? Yes? So that's going to be our function of x. It's going to be our y. Okay, so let's attach this to something that we already know. So if I were to write this, the f of x is equal to x, I bet this would help me to determine what my y is if I know what my x is. So if I plug in a 1, what's the f of 1? 1. What's the f of 2? And 5. Okay? So in general, this is just connecting. Instead of n and a sub n, it's x and f of x. They're the same thing. Okay, so we are supposed to find their sum. So we're going to take it from a sequence to a series. So we're going to go 1 plus 2 plus 3 plus 4 plus 5. We're going to add them up. Now remember my little shortcut for adding a list of numbers? Add the outsides. That's 6. Next set also adds to 6. And then if we add another set, it'd add to 6, but we only have half a set, so it adds to half of 6, 3. That's 12 plus 3, that's 15. When you have a large set of numbers that you have to add, that's a really helpful tool. Okay? All right, let's go to the next one. You have 5. That's a constant. I don't see a variable. So you know what that means? My a sub n equals 5. All the time, it's 5. There's no variable. That means it's unchanging. So it doesn't matter what position it's in. 1, 2, excuse me, 3, 4, or 5. It's always going to be 5. So if I had to add that up, I don't even want to write 5 plus 5 plus 5. Can't I just write 5 times 5? 25. So there's our sum. Because remember, multiplication is just a shortened addition. That's all it is. So shorten it. Okay? All right, let's look at the next one. So now we have C, which is asking us for the first 5 terms of -2 raised to the k. So this time it's k, not n, not x. Doesn't matter. We're going to plug in a 1, a 2, a 3, a 4, and a 5. We're going to get the a sub k, whatever that is. So if we plug in a -2, 1, what's -2 to the 1? -2. What's -2 squared? And -2 cubed. -8, you got it. And -2 to the 4th. Guys, you're multiplying times -2 every time. That's your base, -2. So it's -8 times -2? 16. What's 16 times -2? -32. It's just multiplying times your base. Okay, geometric sequence here. All right, so we have to add it up. So -2 plus 4 minus 8 plus 16 minus 32. Alternating signs. Again, probably easier to add them in pieces. So that would be -34 plus 20 minus 8, -22. Okay, and then we have our last one that says 2n minus 1. So this is in our typical sequence or series notation where our n, or our position, is n. So our answer, our a sub n, so we're going to plug in 1, 2, 3, 4, our domain, and 5. And we've already done this little sequence before. 2 times 1 minus 1. 2 times 2 minus 1. 3 times 2 minus 1. 5. 2 times 4 minus 1. And you know the last one is 9. Because you're multiplying, it's going up 2 every time, right? Up 2, up 2, up 2, up 2. That's times 2. And then minus 1 to get it down to the first position. So we're doing 1 plus 3 plus 5 plus 7 plus 9, which of course you can add in your head as you go, or you could add your outside numbers. 10, 3 plus 7 is also 10, plus 5, total 25. So basically you're asking for a series by adding the terms in your sequence. All right, last thing. What is an alternating infinite sequence? It's not finite, it's infinite, going on forever and ever and ever. What is it? Okay, it's a series in which the signs alternate between terms. For example, did I put an example? I put an empty space, right? So for example, I could do -1. No, let's do -3. -3 plus 6 minus 9 plus 12 minus, okay, we're going to do an infinity, but we're not going to do the ellipse down here at the bottom. We're going to put it right up here because I'm going to interrupt it. Plus negative 1 to the nth position times 3, because that's how it's changing, yes? By 3s, times the nth position, plus infinity. Where at first, what you're getting is the series, where the signs are switching. See it? Negative 3, positive 6, negative 9, positive 12. So the next one would be negative 15. And then you'll go to infinity, and then you'll be interrupted with the rule that helps you to determine if I wanted the 10th number in my series, I could plug in a 10. So what number is the next in my series? What's the position? That's position 1, 2, 3, 4, 5. So we know it's supposed to be negative 15 based on our perception of what's happening here. Let's test it. Negative 1 to the 5th, position 5, times 3 times 5. Well, what's negative 1 raised to an odd power? Negative 1. And negative 1 times 15 is negative 15. So this is what we call an alternating infinite series. Now, it could be finite. I might ask you for the first 6 terms or the first 10 terms. You never know. But it's asking for infinite, so you can see that how it's written out, and you can read it and interpret it. So let's just answer these 2 questions. It says, tell whether the series is an alternating infinite series. So yes, it is, or no, it's not. So let's look at this one. You have negative 2 plus 4 minus 6 plus infinity interrupted by the rule, negative 1 to the nth times 2n. So what's the next number in our series supposed to be? 8. And what position is 8n? 4th position. So if we go negative 1 raised to the 4th times 2 times 4, just by plugging it into the rule, we can tell if it's going to be, it's going to give us what we want. So what's negative 1 raised to an even power? 1. And 1 times 8 is 8. And that's what we wanted. And so we can say, yes, it is an alternating infinite series, or alternating infinite series if you prefer. However you want to write it, doesn't matter. You just write yes. It is. Okay. Now let's look at B. So we have these variables. Now here's the thing. Variables can represent positives, negatives, imaginary. They can represent all kinds of things. So let's look at it. It's b plus b squared plus b cubed to infinity interrupted by the rule b to the n power plus to infinity when b equals 5. So how are we going to know if this is an alternating infinite series or just a regular infinite series? We plug it in. 5 plus 5 squared plus 5 cubed. I think that's 5 plus 25 plus 125, and I don't see alternating signs. Do you? So the answer to this is no. But I do want to caution you. Listen, just because in the first one we could see with our eyes alternating signs, and then the second one it was addition, 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 you can't assume that if it's always going to be addition, that it's not an alternating infinitive. Let's change the question. What if b equaled negative 5? Would it be alternating? So you would test it. Negative 5 plus negative 5 squared plus negative 5 cubed, etc. That's negative 5 plus positive 25 minus 125. So in that situation, it would be alternating. So don't make assumptions, because you know that's never a good thing. Always justify and prove. All right? So there you go. And that's the end of the lesson, which was a long one, almost 40 minutes long. You are going to do problems 9 through 36.